name is Zach Semke, and I'm Director of Passive House Accelerator. We're very excited about today's episode. Passive House Accelerator is a place for information sharing about passive house design and high performance building. We welcome all comers to our exploration of how to slash the greenhouse gas emissions from our buildings and make them more resilient to the wild weather, the extreme temperatures, and the grid insecurity caused by climate change. And retrofits are extremely key to that work. And so we're particularly excited about today's episode, focused on waterproof, breathable fabrics in low carbon EnerPHits at scale, and featuring guests Andrew Simmonds and Tim. I want to first say thank you to Hugh Wariski and Yulia Potor for co-creating this series with the Passive House Accelerator. And I just wanted to give a moment for Yulia to say hello.
Hello, and thank you to everybody for joining us for the third episode. I just want to say that this session will cover innovative approaches and some of the best practices for scalable retrofitting to EnerPHit standards. So stay tuned to learn more about it and address your questions. Thank you.
With that, I want to hand it off to our co-hosts. We have today Dara McGowan of Partel, and Mike Jacob of Kiss House, and Ben Adam Smith of House Planning Help. So Dara, Mike, and Ben, please take it away.
Thanks, Zach. So yeah, my name is Dara McGowan. I'm a technical consultant here in Partel. We supply products for low energy buildings, both for new build and retrofit. So I was lucky enough to get to visit the project we're going to look at today a couple of months ago. And it was really exciting to see a different approach to retrofit. So I'm really looking forward to today's presentation to see the progress that they've made since my last site visit.
Thanks, Dara. My name is Mike Jacob. I'm a co-founder of Kiss House. I'm very happy to be here. I think we're in for a treat. I get the impression there's an awful lot of thinking and a lot of data and a lot of information that's going to be shown to us and shared with us today. I'm really excited about that. Thanks.
And I'm Ben Adam Smith from House Planning Help, and I have the honor of introducing our guest today. I will, just before I do this, say a big thank you to the AECB, who I'm sure we're going to hear a lot more about. But when I entered the world of construction about 10 years ago, I was very lucky that early on someone said, oh, you know, I hear what you're interested in. You should really go and check out the AECB. And it has been a cornerstone organization to the knowledge that I have learned. So Andy Simmonds is an architectural designer and partner in Simmonds Mills Architects, as well as chief executive of the AECB that I've already mentioned, the Association for Environment Conscious Building. His architectural and building experience covers historic and contemporary buildings, innovative and traditional materials, and the development of built environment energy efficiency solutions. Andy has led the development of the AECB energy standards and initiated the AECB Carbon Light program. This makes him an expert on best practice in moisture robust energy efficiency retrofitting of different types of UK buildings. And that also includes one of his own that he did probably some time ago. I'm sure he'll tell us about Grove Cottage. Tim Hulse is a passive house champion and director at EcoVert Solutions, a UK-based company. As a chartered engineer and certified passive house designer, Tim has a keen focus on sustainability and energy efficiency, being a passionate supporter of high performance building. He's been involved in many low energy projects with a detailed knowledge of building physics, focus on the latest sustainable materials, quality, and reduced energy consumption. Take it away, guys.
Okay, over to me, is it?
Did you not like your introduction?
I loved it. It's just I thought that
well,
Zach
it's your turn now.
I thought Zach was going to do this first slide, but that's fine. No problem. Okay, so we're going to cover quite a lot of aspects of things, and there is a danger that you're going to see some intriguing numbers and detail which we just don't have time to get into. The plan is that after I've done this presentation, and when we get some more monitoring data to substantiate what we're saying, we're going to run another webinar where we can spend an hour going into more detail. And also at that point, I would be happy to share this PowerPoint. So forgive me if it appears we're sort of perhaps rushing over some things that you might want to ideally dig into. So yeah, so this is one retrofit project of several in the able to pay private sector, and it's for a 1950s house, detached house near Monmouth in the UK. We've been working on it for the last 18 months in terms of design, and then Tim has been managing the build for what seems like quite a long period of time, but that has been affected by COVID and Brexit, which has added joy to all of us, really. What we're trying to do is work in a slightly different way at the moment. We're calling it the better building model. Sounds rather grand, but we're just trying out a slightly different arrangement. So while Simmonds Mills do the architecture, in this case, it's not just a straight retrofit, it's a rebuilding of an extension, a substandard extension on the end there you see had to be knocked down, and also quite a lot of remodeling internally and a lot of rejigging of windows. So whilst we do the design, working with the client, we've moved to working with Tim much more closely to tighten up the specification based on getting better feedback from products that have worked well and that him and his team are happy to use. But importantly, rather than going to a QS, we've actually worked together to produce a cost plan, open book, so we can be very honest and open with the client. And rather than building in overheads, builders overheads and profit, we've taken that out and tried to sort of present that as a project management cost, which Tim will probably want to comment on in a minute. And as part of that cost planning, we allow for one iteration of value engineering. Obviously costs tend to come in usually beyond what the client is expecting. So to have an open book value engineering process not only produces more resource efficient designs, but it also helps the client understand and also potentially reduce their expectations and the budget. And then the project and site management, as I said, is something that we've sort of asked Tim to price for as a separate service and a separate contract for the client. Tim, do you want to say something about how you found that process, whether you think it's working for you?
Well, that process went pretty smoothly. I mean, I enjoyed working sort of interactively with Andy during the design stages where he'd be using SketchUp or something on a screen, and we'd walk through potential options for the design, and then he'd draw it, and I'd say, well, how are you going to build that? Or, you know, we'd comment on different things and try and figure out how to do it in a way that was could be easily explainable to another builder and easily built. Because the whole idea here was to take somebody who hadn't built a passive house before and get them to the point where they could actually deliver a passive house. Although we're not getting to certified EnerPHit standard on this job, but that was the objective. So the interesting thing for me was how we could tighten up that whole process, streamline it, so that we could present it as a package to people who might be interested in actually doing the work, and then use that to guide them through the build process.
Yes, yeah, there are other interesting conversations around what we're trying to do there, but I don't think we've got time to do it, unfortunately. So if I move on. I was particularly interested in this project because
we are thinking of getting much more involved in retrofit. We've obviously been focusing on it for a few years, but it is so hugely important and hugely challenging. Every building is different. We have not only energy issues to deal with, reducing the energy we use in buildings, but also embodied carbon issues. And there is a real need just to sort of really start exploring, and but exploring in a rigorous way. So, you know, we do PHPP to look at the energy performance of the building before and after retrofit, but also we're using PHribbon to do lifetime carbon calculations, so we can start to make intelligent decisions about whether we use this material or that material, looking carefully at trade-offs with operational energy versus upfront carbon emissions from products. So one of the reasons that we ended up so enjoying this as a technical challenge is because we're looking, how do we use low cost, easily available timber-based products used very efficiently in very small quantities to achieve very good U values. So for example, the walls in this construction, as you see, are very fat. The external wall insulation system is very fat, achieving U value of about 0.1 through using recycled cellulose insulation, very small section timber, wood fibre boards and so on. So at a technical level and a sort of reduced embodied carbon level, it's a very satisfying project. And the client was also particularly interested in this. Not only did he want a very low energy building, he wanted to explore innovation, but meaningful innovation, not novelty. So we found ourselves aligned on that. The standard that we were aiming for on this project was initially suggested by the client as EnerPHit, so the passive house standard for existing buildings. And we said, fine, you know, no reason we can't achieve that. And that was the initial target. So all the measures that we're applying to this building were designed to achieve EnerPHit. But we did have a separate conversation, which was that an equally meaningful standard for the UK for existing buildings is the AECB retrofit standard. So that's the Association for Environment Conscious Building. And it's slightly less demanding. We also think that it's perhaps more replicable across all the different types of buildings in the UK, particularly housing. And we said, let's use the AECB standard as a backstop. So at the moment, the Passive House Planning Package, PHPP, shows that the measures we're applying here pretty much deliver EnerPHit in terms of the thermal performance. It's hovering around the target number for space heating demand. What we're less sure about is the airtightness target. So what we've done is use the AECB standard target, which is two air changes per hour, 50 pascals, as our backstop. And that's what we're looking at today. Where are we? Have we achieved the backstop? And in fact, can we improve it? Maybe even to get one, which is of course the EnerPHit target.
Andy Simmonds came to me with a client who was interested in doing something with it in a really low carbon way. And I've done a number of projects with Andy in the past. We've done two certified passive houses and a retrofit. And I was really interested in working with Andy again. But what we were looking to try and do was come up with a system that we could use on multiple projects. And off the back of this one, we've got another 2 projects that we need to do. Now, all 3 were going to be pretty similar. We wanted to standardize on a solution that we could take from one to the next and possibly send out into the wider world for other people to adopt as well, not just something that we would keep our arms around. So I was involved with Andy pretty early on in this project, trying to figure out how we were going to do it, and we agreed that we'd do it in a collaborative way, which worked really well using SketchUp and Zoom online, sort of designing in real time, trying things out. Andy would draw something and say, well, what about that? And I'd say, well, how are we going to build it? Or if we did that, it would make it easier. So it's really sort of interactive approach. And very early on, we decided that we were going to approach it by trying to wrap the house from the outside using I-joists. I'm particularly concerned about us using sustainable materials. Whilst we've used EPS and other plastic-based insulations in the past, I'd much rather move away from them to more sustainable materials. And stuff based on wood
just seems to work really well. We've built a few houses with I-joists and filled them with warm cell insulation. So we thought, well, why don't we take the same approach here? So what we've done is simply wrap the house with I-joists up the outside walls, over the roof, filled that whole space with warm cell, which gives you a nice insulated tea cozy effect wrapped around the house. And then the next part of that was trying to think how we're going to finish that on the outside. And typically in a new build, we'd put some wood fibre insulation outside of that to break the thermal bridge through the I-joists, and then put membrane outside. But Andy was concerned about bats and catching the hooks on the membrane. So I suggested putting the wood fibre outside instead of the membrane, which is what we did. It sounded simpler than it was. It's simple on paper, but it created some issues in terms of actually getting the warm cell into the building, and when we came around to the practical side of it, which needs a bit more thinking about next time. But overall, it worked really well. I think we've ended up with a good, solid, deep layer of insulation right around the house, wrapped with the membranes and then the wood fibre on the outside.
The interstitial condensation risk is right here, right on the cold side of the insulation behind the membrane, and particularly because there is no specific air vapour check on the inside. So I guess this is what makes it fairly innovative. So in order to assess the risk, we asked Partel to carry out a WUFI calculation, looking at the worst case, and we thought maybe the worst case was what might happen to the metal fixings holding on the wood fibre cladding, because if condensation was forming around those nails in cold winters and creating little rot pockets, the whole thing could fall off. So we identified a weakness, a sort of weak point, and then assessed that. The WUFI suggested that we should be fine, particularly because we're using cellulose insulation. We certainly wouldn't try this with a mineral fibre or another non-hygroscopic material in the wall box there. Now, in addition to that, WUFI is fine, and it can certainly capture trends and give us a good indication. But we have a number of projects similarly trying out different things like this, and about 20 projects where we have environmental condition sensors built into the constructions. So we decided we'd do the same thing here. So we have a number of sensors on the warm side and the cold side of this construction. We have one inside and one outside the building, and we can basically follow it over the next year to see exactly what is going on here. So we'll be measuring relative humidity, temperature, and also the moisture content, wood moisture equivalent content, WME, of the critical timber members. So those are in now, and we're starting to get readings, which is very interesting.
One of the really interesting things about the project is that we've essentially taken a local builder who's never done any of this stuff before and strong-armed them into taking that step up to really trying to do something different. And there's so much different about this project, compared with how people would normally do, improve their insulation on a new build, on an existing house and so on. Generally, if you go and if you have an extension built, so you have some work done on your house, you don't think at all about airtightness. That's completely unknown to regular builders, and they'll typically put much less insulation on. It's probably just kingspan dot and dabbed onto a wall and something like that. So everything about the way that we've done this is completely different. We were lucky with the builders here. They've had some experience with timber frame, which has really worked out in terms of putting the I-joists on the wall. It's in a way, it's just like big timber frame. But it has been a big learning curve for them in terms of trying to figure out how to do the airtightness and so on, that we've tried to help them through. But at the end of the day, you've just got to do it, see what the issues are, and figure out how to deal with it. And the lads are really engaged with that. They've really got stuck in. They're thinking about how to do it, where the issues might be. Asking questions, which is, to me, that's 90% of it. If you're thinking and asking questions, you're going to catch most of the issues. And then it's our job to try and point out the more tricky things that people typically wouldn't think about or would gloss over. But the importance of doing it at this stage in the build is that you've got the opportunity now to try and correct things. On the outside, you know, we're pretty much a bit limited in what we can do. Most of the cladding's on the building now, so we can't go back and do anything there. But outside, it's relatively straightforward. It's big sheets of membrane taped together, so it's not an awful lot to go wrong there, apart from nail penetrations and screw penetrations. But for me, the tricky bit really with any retrofit is this sort of blend between the new work that you're doing and what's already there, what condition those walls are in. And the walls here, I think it's a 60s house, but the construction it's not in great shape. The mortar isn't great. It's got some really poor quality concrete blocks in places and things like that. So it's a very porous structure. So basically, as soon as anything gets to hit that structure, there's a good chance that it's going to be in and around and come out somewhere where you're not expecting it. So I think if we can get sub 2 on the air test, I think that's good enough. You know, considering that the project as a whole isn't trying to get down to passive house levels of insulation and everything. We're taking a balanced approach, and I think sub 2 on the test is going to be where we need to be.
So I'm Gervais Manguana. I'm the air pressure tester for the project. This is the first time I've visited the site today, and we've agreed a 3-test strategy for this project if it was needed. And initially here we're effectively testing the external air tightness layer, which is a bit of a novel approach on this project. And ultimately, I think the ultimate aspiration would be a EnerPHit level 1 air change target, but with a backstop of an AECB 2 air change target. And there's still a fair bit of work to do in here. And there were some things that needed sealing up, the usual penetrations and so forth. So on our first test, we got to around 3 and found a few things that still needed sealing, some soil vents stuff that got missed. So at the moment we're down to 2.4 and we're just going through some of the other non-intentional penetrations that have been discovered on that first sort of test, and see where we get up to at that point. Feeling engaged and wanting to do more. I just asked the builder here whether he'd do it again, and although he's found it difficult and challenging, he totally does want to do it again, so that's great to hear.
Okay, there's been some interesting chat actually in the very sort of socially relevant chat, and I think I will try and tackle some of those or respond to some of those issues as we go through, because certainly our focus is on the ethical and social aspects relating to this. So although this is a sort of relatively high budget project, not all of our projects are by any means, and this is a very good test bed. Certainly the client, who is an engineer, is very interested in helping us make this a test bed. And since we started this project, we've won a contract to work on a social housing program under a new British standard, which has tried to introduce quality into retrofit for social housing. And so obviously a lot of what we're doing here, we're hoping we'll be able to feed into that sort of work as well. So this kind of touches on it as well. So what is the scale of the challenge? Well, if the challenge is to improve the performance of pretty much all the buildings in the UK, I mean, it's the UK context, then the challenge is immense, because our buildings are very poorly performing buildings, and we spend an awful lot of energy keeping them fairly cold, in the sense that so much heat leaks out, and that has health impacts, and it has greenhouse gas impacts, and as far as we can make out, it's a sensible response to climate change, is to try to do something about it. Doing something about it is not something we've been very good at, because the energy efficiency programs that have been implemented suffer, among other things, from doing too shallow a retrofit, which doesn't help alleviate fuel poverty. It doesn't take much increase in fuel costs to sort of push people back into fuel poverty if you don't do enough deep, you don't make a big enough improvement. There are also sort of unintended consequences to do with poor performance. Health, particularly indoor air quality, can suffer. moisture related problems sort of start surfacing. And certainly in terms of greenhouse gas emissions, the measures just don't deliver what we expect them to. So there's a serious issue here. So the way we look at this, I mean, a fun fact, if you want, UK houses might be described by types. The Building Research Establishment has 13 typical buildings. We found it useful to group those into 3 categories described by the form factor, the sort of proportion of heat loss area to the floor area, and the higher the form factor, the more difficult, the more challenging it is to reduce the heat loss cost effectively. So you end up having to sort of achieve better U values on high form factor buildings like bungalows. Medium form factor might be a typical semi-detached or end terraced house, and a low form factor would be something very compact. So a mid-terraced 3-story townhouse would be a good example of that. So from the AECB domestic stock model, which we've built, we actually have a fairly good idea of some sort of key characteristics of our building stock. So in England and Wales, for example, there's about 2.5 million bungalows, 10.5 million semi-detached houses, and 12.5 million townhouses. Now, if I got my rushed late night sums right, taking the figures from that, that's about 900 square miles of wall surface that probably needs, well, almost definitely needs insulating, but being realistic, because of various other constraints, maybe a third of those properties might have to be internally insulated because of conservation issues or boundary issues or other complexities. Maybe 1/3 we won't be able to manage, either because they're listed or just because the programs just can't scale up enough. Even if you were to say a third of those properties might need some form of external wall insulation, that's about 300 square miles of wall, which we need to, arguably insulate between now and, let's say, a notional 2050. So that's really starts to make you think. So some of the obvious things that jump out of that is that, well, there's no one particular approach. We need a variety of approaches. We need a wide range of EWI systems, and they should all be focused on trying to, from our modelling, reduce the space heat demand of the UK stock by about half, down to something like 50 kilowatt hours per metre squared in a year, bearing in mind that EnerPHit would be looking at around 25 kilowatt hours. So this is we've actually pitched the AECB standard around this. So some projects where the opportunity allows, we should do better retrofits, and the more challenging projects we might do slightly worse. But on balance, on average, if we can get our space heat demand down to about this level, then the forecasts given to us by the national grid as we decarbonize electricity and move a substantial portion of domestic heating over to electricity, then the national grid reckons it can provide that amount of decarbonized electricity for to cover space heating out to 2050. So it's supply and demand matching. Getting a typical UK building down to 50 is still challenging. We need to avoid performance gaps, because basically, climate change is a physics issue. We can't have performance gap; it has to perform, and we can't have systems which are vulnerable, particularly to moisture damage or other failures. So they have to work well. We're definitely going to need the materials we use and the processes we use to manufacture and on site to become increasingly decarbonised. There are going to be supply and demand problems. I mean, we're seeing it with Brexit and COVID related factors, but obviously as we scale something up, to levels of construction that we haven't seen for many decades, if potentially if ever, there are clearly going to be supply and demand problems, and that also applies to skills. So systems need to be fast and relatively easy to understand, and so on. And obviously, big picture, we need enough material resources to be able to actually carry out programs at this scale. A few headline figures about this particular project. So it's 175 square meters. It is currently showing that it should achieve the EnerPHit space heat demand target. The air test, following Gervais's test that you saw in the video there, we did that at a point where we hadn't completed for example, the floor to wall internal air tightness taping. We haven't completed that. So we on the following test, we perhaps surprisingly found we got down to 0.75 air changes per hour. So actually we have achieved the EnerPHit, and that's through the measures that I'll describe in the presentation. I've just quickly shown the the losses and gains associated with this house, just because there's always a couple of interesting things in there. So you can see that the windows, which are this yellow block, the losses of 17.8 are about the same as the gains, useful solar gains. So on balance, the windows don't gain much more than they lose, but and vice versa. So it's not a bad balance. The brown there on the left, the 5.1, shows that we've actually reduced heat losses from the floors quite well, but we have had to go in quite heavy with that one. We've dug out the old floors and we have replaced it with a fully insulated new floor. So there's a carbon upfront carbon emissions associated with that. One of the things we were trying to ensure happens is the surface temperatures of the wall to floor junction are high enough, because one of the biggest failures of not treating the floor is where you get thermal discomfort, and people will tend to turn the thermostat up as a result of that. In terms of strategies, so the section on the left shows the house, cavity wall construction, which had actually had cavity wall insulation in it. So there's some graphitized grey polystyrene beads in the cavity, but otherwise a pretty basic tiled roof construction, solid floors, no insulation apart from the cavity there, and I think there's about 4 inches of insulation in the attic. So you can see, again, it's sort of a substantial intervention where we've put the I-beams over the top of the existing roof. Just going to hide those controls, right? Over the top of the existing roof, we've put I-beams on the outside of the cavity wall insulation, and we've renewed the floors, and we've also taken some insulation on the outside of the walls down into the ground there. Then the air tightness strategy, which you can see on the right, and we haven't done this before, is where we, for reasons that should become clear as we go through, we wanted to wrap the house with an air tightness layer, which is the Partel membrane. And obviously that has to allow water vapor to escape. So the red lines down at the bottom right hand part of that screen show you the elements that are airtight in a sort of more conventional way. So the new concrete slab, which is in there, the mass of that's the air tightness layer. That is taped to the masonry inner skin wall. So that's a fairly robust airtight detail. We've had to assume that the cavity inner leaf and then the polystyrene bead insulation and the outer brickwork cavity wall, we have to assume across there is generally fairly airtight, because you can't get to that, and we just made that assumption. The vertical red line on the outside is a combination of a tanking layer to prevent moisture getting into the plinth insulation and to provide a bit more resistance to the outside part of the wall, but it's also an air tightness measure. And then the blue line basically shows where the membrane goes from the masonry wall, along the underside of the I-beam system, up the wall to the windows, and then back up over the roof and so on. So it's an external air tightness wrap. We did limited air tightness measures on the inside of the building, but you can see we did decide to plug the biggest holes inside, and particularly where the sort of first floor joist there had sort of loose sockets into that area. We thought since we had the opportunity, we would just foam that. Okay, so these are the elements, basic elements. Down at the bottom there, we have a sole plate, and that was a site-made I-beam, sheet of plywood, 2 pieces of 2x2. Number 2 are the brackets. So we had some fixing brackets, 2 different sizes. Number 3 is the placement of the first piece of air tightness membrane sealed to the wall and then left ready to lap to the membrane later on. 4 are the vertical I-joists used as wall studs, and they're at 1200 centers in order to minimize how much timber we were using. Item 5 is the 2x2s running vertically at 600 centers. 6 just shows you the volume that was had the cellulose blown in. 7 is the air tightness membrane. 8 is the wood fibre insulation. 9 shows you the vertical counterbattens, which gives you a drainage and ventilation layer. And then 10 is your cladding options. So this design started with sawn Western red cedar ventilated rain screen, which we've done on other projects. In fact, we're doing on the next project. The client in the end decided to go for a fibre cement interlocking board, which obviously carries a higher embodied carbon penalty. Just shows you the build-up of the U value there. So we've gone for a very low U value using a 300 mil eye stud. The next job we're doing, we'll use a 220 eye stud, but even with a 195 eye stud and factoring in the thermal bridging of the timber, we can still get, you know, a typical passive house U value of just under 0.15. So as part of the project, the client wanted to demolish certain adjacent structures, so sort of porch, the extension itself at the end was demolished because the blockwork was, once the plasterboard was off, you could see there were some major cracks, which he was worried about, so that was demolished. But he did want to keep an oak frame extension, which had to be incorporated into this system. The roof was rebuilt at one end to form a gable at the client's request. You can see on that sort of internal shot there that the internal face behind the various plasterboard linings, there was all sorts of stuff going on, and some of that involved moving windows around. And then on the two bottom right there, you can see the I-beam construction for the extension just being started. So in terms of like individual components for this system, the I-beam is something I'm sure you're all familiar with. Softwood flanges and an OSB web piece glued in. To create the new overhang, having wrapped the building in these I-beams, to create the new overhang and give the impression of rafters, we used false rafters, what we call them, and we actually tested those by fixing them to a wall and everybody hanging off them to see how strong they were. They're perfectly strong enough. On the bottom right there, you can see the membrane having gone on and the wood fibre board. These are the brackets. The engineer on the job, he worked out the sort of worst case loadings on this system and gave us some rules of thumb. Basically, it was written down on a drawing, but just a sort of indication of where these brackets should be placed and maximum centers and so on. Tim, I don't know if you want to mention anything about that tricky detail there where we had to put on an airtight seal behind that structural work.
Oh, Tim, I think you're muted.
Probably saying something.
Sorry,
unflattering.
The only really was that the order was done wrong. The membrane should have been taped to the wall before the base plate went on, and it wasn't. So just adds extra complexity if you don't do it in the logical order.
Yes, I think the contractors learn very fast, though, don't they? Once they've been through that and made a couple of mistakes,
yeah,
it gels. Yeah, I think this, Tim, is another question for you. Is, you know, here it is a sort of minimal timber use framework on the outside, and it was designed to use very little timber and to be fast. And I think that's one of the things that you liked about it. Is that right?
Yeah, and although the diagram Andy showed earlier showed 10 different parts or components of this overall build-up, if you look at it as in that photo there, it's actually quite straightforward. There's half a dozen I-joists and a bunch of 2x2 holding it together with some ply on the bottom. So getting that across to the builder wasn't hard work. And once they got started, they just flew through it. So in terms of a system that you're trying to get people to adopt who aren't familiar with doing things in different ways, this ticked the box. They picked it up quickly and they were able to build it fast.
Yeah, great, thanks. So you can just see these aren't components, though, but it just shows a bit of detailing. And I'm really showing this because as we move towards more timber-based products, we're particularly concerned about not forgetting brick construction is very good at keeping the rats out, basically, and it's something that we really shouldn't lose sight of, that rats and other rodents, other beasties are potentially quite a a problem. It depends on the insulation you use to some extent, and also the sort of ground conditions in terms of tunneling distance. There's quite a good American website I came across about how to design buildings to discourage rats from getting in. So again, just looking at some of the thermal modeling we did, this is to ensure that the comfort conditions at the edge in the living rooms and the studies where people sit for long periods of time are warm enough. I won't go into the building physics of it, but Passive House has got very good, solid evidence as to why small temperature differentials from the ground to your shoulders when you're sitting down can cause discomfort, even if the room temperature is 22 degrees, air temperature is 22. And we've seen that, we felt that in practice in various previous projects, so we take it quite seriously. In terms of value engineering, there is some scope in looking at whether the plinth insulation should, on the outside of that EWI system, needs to go into a trench in the ground. Could it not go to the ground? And the social housing project we're working on, the contractors are asking us to look at that. And so if we can get the results we want without having to dig trenches around the outside of buildings, clearly that's a very sensible thing to be looking at. One of the final components here is the window boxes. So you can see from the lower, from that middle bottom slide there, when you take off the linings on the inside of some of these homes, there's a chaos of stuff behind. It's a palimpsest. I know Lloyd Alter, who's here, likes that word, but it's you know, the layers, the historical layers of work that people have done. And we basically tried to not do anything in terms of airtightness, expensive parging, not only because of the time and the labor, because cement layers actually carry quite a high upfront emitted carbon cost. So we're trying to cut out cementitious layers wherever we can. It all adds up. But you can see that the idea was that the plywood window boxes, FSC certified plywood window boxes, were made up to a schedule to take the window units when they arrived on site, and they were basically installed through the chaos of the old building and out to meet a datum line, which is the outside of the I-beams. So on the bottom right there, you can see that some of the sort of tumble down, broken parts of the wall, however that might arise, doesn't matter. That just gets all absorbed by the cellulose insulation when it gets pumped in. So in terms of identifying where these risks are, I mean, are there any risks? Is this system risky? We've from previous research, we've seen that if this was mineral fiber insulation, we would be much more concerned about the interstitial condensation risk on the cold side of that structure where it meets the wood fiber. So you've seen that Partel did a WUFI for us, but we've also got these data loggers in to give us a environmental condition profile through the building, which we're sort of getting quite used to doing now. And that allows us, particularly if we identify the areas of risk we're worried about, or might be worried about, is to look at whether during construction, during the drying out phase, and during normal operation, whether any vulnerable elements like timber exceed critical thresholds. So, you know, sort of moisture content, humidity, temperature can all combine over time, over certain periods of time, to put these timbers at risk. So this is what we'll be doing once we start getting the data in. So here you can see bottom, basically we chose a wall which is going to be most likely the worst condition. We did take it away from the DPC level, so it's about a meter up, but it's on the north facing wall, so we don't get any benefit from solar gain sort of helping the moisture balance. So it's on a shaded north facing wall, and we've put sensors into the masonry behind the old render. We've put it onto the timber flange right next to that, and we put it onto the timber flange on the cold side, and we've also buried in the cavity wall insulation the same type of wood with a sensor on it as well. So we'll be able to look at the different environmental conditions through that wall construction and then analyze it. And we started getting data, as you can see top right. This is an unheated building without the MVHR system installed at the moment. So once that heating system once the heat pump is turned on, you will start to see these graphs separate, because you're going to get more sort of warmer structure on the inside relative to the outside. And then finally, I think this is the final one. Yeah, final two slides. This is previous work we did with Passive House Association Ireland, where we used the PHRibbon that was mentioned earlier to look at elements of a typical Irish building regs house based on a local authority's specification. And we worked with Jeff Colley of Passive House Plus to look at incremental changes and then more significant changes to take some of these elements into lower carbon ways of building. Cut a long story short, we found it a useful exercise, and you can see that moving from a masonry cavity wall out to a timber frame wall can potentially bring down the impact for that particular house from changing the wall construction from 25 tons to 14.5 tons, arguably with other benefits as well. And as part of that, I'm not going to get into carbon accounting because it's too fast paced to do so. But in terms of that, some of the carbon that involved is actually stored in that assembly until such time as it burns down or it's recycled or it's dismantled and so on. So normally that is we assume a 60-year life cycle. You can change the lifetime assumed for the building, and within that 60-year building lifetime, different components will have different lifetimes. So this program actually calculates, how many times a heat pump has to be sort of replaced and so on. And what we're thinking of doing with this project, this is the final slide, what we're thinking of doing with this project is developing a bit of a ready reckoner. So we're actually working out the upfront carbon, which is stages A1 to A5, upfront CO2 emissions. We're looking at how much carbon is sequestered or stored in the assembly. And then we're looking at sort of the end of life implications, because what happens at the end of life is unknown, but there are standard assumptions. And our Royal Institute of Chartered Surveyors assumes 75% is incinerated and 25% is landfilled. Now, as designers, we can help change the destiny of these components, what happens to them, but we obviously it's a long time in the future. So you have to have some assumptions. Over here on the right, as part of the standard lifetime carbon accounting, you can, what we're trying to do is encourage designers to think ahead so that making things easily reusable, maintaining the value of these timber components so that they will more likely be reused, avoiding composite products which are hard to repurpose or reuse. So this thinking does need to happen now, and this is something we really want to encourage. So we'll be firming these figures up, but you just get a sense here of how each component carries, is responsible for upfront emissions. And the idea is that if somebody wants to adopt this system, they can just measure the linear meters around the building, they can measure the square area, and then give themselves a sort of rough idea of what the upfront embodied carbon emissions might be from applying it. And we may do some comparisons with, for example, polystyrene external wall insulation and so on. Thank you.
That was really interesting, Andy. Plenty of data to think about there over the next few days. I have a half a page full of notes here and stuff I'm going to follow up with. But one particularly jarring point I thought was the 900 square miles of wall surface that we're going to have to deal with in the UK. And we have some similar, I suppose, scary targets here in Ireland. So we're looking at 500,000 homes to retrofit, and it's quite a challenge that we need to face. So I work in an advisory role in the Centre of Excellence for Retrofitting here in Ireland. And as part of that, we're looking at EWI. And I think it's a really important point that we can't overlook. Number one, of course, the embodied carbon, which you just touched on, but the workforce to get people to do that to 500,000 properties is going to be a real challenge for us here. And I think the word you used was variety with EWI. I think that's really crucial to being able to deliver on these targets. It's great to, I suppose, have the desire to do it, but to have the manpower is something else. And I suppose, Tim, it's a question for you. Was there much involved with teaching the guys to work with a system like this? I know with the likes of an EPS system, while there's the embodied carbon issue there, there's also the issue of, specialist installers and so on required. And that sometimes just isn't possible for such a large scale retrofit market. So is that something, Tim, that I suppose required a lot of hand holding, or did the guys take to it fairly quickly?
No, it didn't really, Dara, to be honest, because they'd had some previous experience with timber frame. They're mostly used to working with masonry construction, but they'd done some timber frame before, so they built stud walls. So, they quickly grasped the concept that basically it's just a bloody big stud wall fixed on the outside of an existing building. So that was fine. And then putting the membranes on, that was simple. They're used to using vapor barriers before. Wood fiber is just like putting plasterboard on. So generally it was pretty straightforward. The complicated bits really were things like getting window boxes right, thinking about the airtightness details ahead, as we mentioned earlier, so that you don't back yourself into a corner where it's hard to fix, harder to address once you've already done something else. But no, generally they didn't find it.
I think it's something that it's something that could be lost in such an interesting presentation, but it's a really important aspect to scaling up retrofit. We're not talking about individual dwellings here. We're talking about lots and lots of work that has to be done. So really interesting, guys. Thanks.
And yeah, I'll just say well done, guys. It looks like a fantastic project. And I know, obviously, your history, a lot of retrofits under your belt now. I'm not sure everyone is exactly in the same place, but it does feel like the knowledge is there. And if we were even thinking about repeatable systems, the number of times I see the same I-beams, warm cell, the wood fiber board all coming together, that does seem like a solution that's used on a lot of low energy projects. I wanted to sort of bring it back a bit to reality, because we've had doubling gas prices quite recently, and I found a few people have contacted me asking for advice. What should I do? Generally, they're thinking along the lines of, oh, is there some magic kind of heater which is going to solve all my problems and cost nothing? But when you start to explain the approach of what you need to do to actually sort things out, they're a bit, well, that's not what I want to hear. That's not the answer. So all those miles of insulation that needs to get done, I think, is slightly trickier. And I don't know, if gas doubled again, which it could easily do, is that going to trigger a bit more? And then I'll also flip it that, we're actually following a retrofit project in the hub at the moment, and it's been a complete eye-opener. But the amount of money that must have been spent, I still don't think this is being reflected in the value of the house. And this is a wealthy area. If you're in a poorer area, that investment is a big investment. And one final thing, my dad he's very keen on making his house more efficient and so forth. But again, it's a similar challenge of he's got the money to do it. But personally, I'm a little bit worried that if he went ahead and did a big retrofit project, given the location where he is, that the next people might not come along, completely ignore what's been built there and knock the whole thing down and start again, which may be a bit cynical, but it wouldn't surprise me. So I've got all those sorts of things going on, but I think the technical side of things, you guys have got covered. And I know through the AECB, you're trying to filter out all that knowledge. So well done.
I just want to congratulate you and thank you. I'm grateful that people like you exist and are doing this. Really, it's a labor of love, and you are going above and beyond what most people do in their line of work. And I'm involved in trying to systematize a new build product, which you might say is easy, relatively speaking. We're doing the best we can in our world, but you're trying to systematize something for retrofits with many of the same values and ambitions that we have in terms of resource efficiency, material use, and achievability and simplicity, and all of these things that we're doing in our easy new build paradigm. And I bow down to the scale of your ambition. I'm particularly interested in the ambition to let go of this. I think if I understood you correctly, Tim, you said something about wanting to get this to a point where you no longer had your arms around it and could release it out there into the world for use by others, I guess, once you've ironed out the issues and developed the system. Is it something you could just feed back on a little bit? Is your longer term ambition for the system?
I'm not sure whether that's something you're better to comment on, Andy. But I think that generally through the AECB, we're planning to have another seminar through the AECB which goes into this in more detail, but it's certainly something we'd be happy to share details with to anybody who's interested. There aren't enough people, you know, this as you saw, there's so many of these jobs to be done around the world. There just aren't enough people to do it. So we're not in a competitive situation right now. We just need to be sharing all best practice with everybody, and hopefully, you know, things will come back, and overall you'll lift the whole boat.
I think picking up on Ben's, you know, perhaps not overly cynical kind of take on this. So it's been interesting for me to be thrown into what was the eco program. You know, let's not be beat around the bush, you know, banging measures, individual measures onto buildings with not linking them up, not overly worried that they work, thermal bypass, air leakage, performance nowhere near what's designed, you know, and sometimes with really serious consequences of damp and mold, with this new approach of a quality assured process, because it's not just about individual technical solutions. I'm sure you all know this, or in, you know, or sort of knowledgeable areas like the AECB or individual people. It's a cultural kind of, its values. And what I'm finding, and it's quite painful, I have to say, working within the delivery infrastructure under this new scheme for social housing retrofit, is the systems carry forward this lack of awareness about performance, or even care about performance. It's just not built into the systems. And so we find ourselves as retrofit designers using PHPP, saying, I know that your SAP said that you can hit this government target, but we're finding that it's more than double what you'll get, and knowing as well that probably it's even worse than we're saying, and they're seeing us as, oh, you nerds using PHPP, and you know, they recognize our knowledge and our understanding, but it's just very alien to them. And whilst if we had 100 years to sort this out, I'd be feeling pretty relaxed about it. Oh, we could keep pushing and we'll get somewhere. But we don't have 100 years. We kind of got, well, we haven't got any time, have we? So the challenge is insane. Now, I'm not saying that, you know, when change happens, it doesn't happen very fast, but certainly, you know, going from the cozy world of projects like this, where the client's really into what you're doing and you're working with other AECB members, to, you know, the rooms full of men managing a small number of builders, and you know, it's a very different environment, and we're going to stick at it. But I have to say, it's been incredibly stressful to be out on such a limb in that environment. And I don't think we're making ourselves particularly popular in some quarters, but the housing associations are, I think, generally more focused on hearing. They understand, because it's their tenants that see the heating bills. So coming back to this system, what we're doing, I think, is useful. It will become useful, but it will only become meaningful if cultural value, if it comes from the top. Politicians have to be absolutely clear. If it was a war and they wanted to win a war, they would make sure they won that war. When it comes to rolling out massive energy efficiency to deliver genuine performance, it's a completely different ballgame. And I can see that coming all the way down, you know, and so until that changes, meanwhile, some of the industry is changing how they do it. They're mobilizing, they're starting to buy into what we're talking about. I say we, as in, you know, doing the right thing. But it's a long process, and it's going to have to speed up. Otherwise, what we're doing is interesting and potentially useful, but potentially meaningless as well.
Well, I know that we've had a lot of really good questions, so we're running a little bit over. And I think Zach, as our man with the questions, how many have you got there?
I have lots of questions. It's been a very active chat, really great questions. So I'm going to jump into that process real fast. Before I do, I want to say a couple of thank yous. Of course, thank you to Andy and Tim for this great presentation, and in advance for your answers to these questions. And thank you to our co-hosts for making this happen. Also, thank you to our sponsors at the Passive House Accelerator. So our founding sponsors are 475 High Performance Building Supply, Baxt Ingwe Architects, Glavel Foam Glass Gravel, Minotaur All-in-One HVAC and Dehumidification Units, Mitsubishi Electric Train HVAC US, Partel, RDH Building Science, Rockwell North America, Stocorp, and Zola Windows. Our champion sponsors are Icon Windows and Doors and SIGA, and our stakeholder partner is NYSERDA, the New York State Energy Research and Development Authority. Thank you too to our patron sponsors, Aero Aggregates, Aero Barrier, BR+A Consulting Engineers, Brennan Airtightness and Insulation, Euroline Windows, Inotech Windows and Doors, Lamelux, Sanderson Sustainable Design, and US Engineered Wood T-Stud. So thank you to our sponsors. All right, so we are going to get into questions and answers, and I normally would have the list queued up for you, but I don't. So I'm just going to throw it out here that the first question is going to be from Stephen Howland. Steve, and I'm going to make sure that Stephen is still here. Stephen, if you could unmute yourself, and you had two questions. If you could choose one of them now, and I'll get back to you for the second one in the queue. Oh, you don't have a microphone. Got it. Okay. So Stephen's first question was, if in 10 years the house is sold to someone else or upgrades are being carried out, when someone is redoing an energy rating, will the owner/client have all the required details to substantiate a non-default U value, air permeability, thermal bridging, etc.? Have you redone an energy rating calculation based off its defaults had it to be used? I don't understand the second part of the question, but I think the part of this is documentation of
documentation is important. Yeah, we haven't yet done the SAP rating, produce the EPC certificate. We will be doing that. Whether it comes out as a B or an A, probably come out as an A. Do you think, Tim?
Yeah, I would have thought
this
so.
one. Yeah, it doesn't sit very well with the Passive House methodology and toolset, but that's one thing. Yeah, clients do need to have information about the building, but particularly and that needs to be in a robust format that lasts the test of time. But I suppose electronic formats, maintaining a link with new owners with the architects is part of that. So they know who to call. Basically, we do building manuals for non-domestic buildings. It tells people how to run it, what to look out for, who to contact if something breaks. It tells you how to fit stuff to walls. If you've done some IWI, people need a bit of guidance on that, because we all forget. Can I do this? Can I do that? What fixing do I use? We haven't done it. We haven't done it for domestic buildings. It's just another thing that we don't get paid for. So. If we were doing, perhaps when we're doing, hundreds of retrofit homes, for example, under this program, we'll have to think of a more coherent way of doing that. Although that is built into PAS, the PAS 2035 process, they do collect documentation. That's the retrofit coordinator's job. So actually, they do have that covered. But certainly in terms of this particular project, I do like approaches to retrofit that takes the air barrier out of danger zone. So if people drill holes in walls or knock a window out or whatever, first of all, they know where it is, very clearly know where it is, but general knocking about doesn't damage it. So achieving air tightness with a bit of plasterboard, and some sort of tape in various hidden corners that easily gets moved around and breaks the air barrier is not a good idea. Ideally, you'd want to retrofit buildings in ways that are just, you can almost, it's protected for 100 years. Air tightness has to last for decades without being compromised. So that's where we need to go.
Great. Thank you, Andy. Okay, so up next is Luke McNeely.
Thank you. This is an awesome presentation. Thank you guys so much. And just echoing what was said before, you are leading the way in a great area. You mentioned concern about using hydrophobic insulation materials in the I-joists, and that was somewhat in context just after talking about the metal fasteners holding on the sheathing. And I have not done any of the detailed thermal bridge calculations or condensation risk calculations. And I don't quite understand why the cellulose is a better choice in that case. I have heard, however, that cellulose can hold moisture more, and sometimes that can be a concern because now it's a moist cellulosic fiber next to more cellulosic fiber. So anyway, I'd love to hear.
It's fairly it's fairly straightforward. So in terms of you know, where does the moisture risk come from? Well, the high magnitude moisture risk is liquid water coming from rain, leaks, floods, whatever, you know. So we're not actually necessarily concerned about that in this context. So take the sort of mass liquid water out of the equation. So then the next level magnitude is rising or penetrating damp, you know. So down at the bottom of this wall system, we were, you know, paid a lot of attention detail to, you know, what are the ground conditions? Is the capillary movement of moisture up through some old DPC, some dysfunctioning, you know, layer of slate or whatever? Because it's fine when there's nothing on the walls, when you've got a little bit of rising damp going on. I think the water vapor can evaporate from the base of the walls fine, but the moment you take out free air movement by putting something against it, even a little bit of rising damp could start to cause some problems. So where the DPC is not to be relied on, we do put a hydrophobic brick cream injection into the mortar joint just to make sure that we don't have problems, you know, 10, 20, 30 years down the line. But then leaving aside and going to the next level magnitude, the sort of lesser magnitude risk, it's interstitial condensation to do with water vapor. So as you probably know, almost all houses in a heating climate like ours, the water vapor pressure inside a house from activities and cooking and whatever is always higher. The water vapor pressure is higher inside than outside. So water vapor is moving through building structures until it meets something that's impermeable. If it meets something impermeable on the warm side, it doesn't matter. If it meets something impermeable on the cold side, it will build up, water vapor pressure will build up and it will condense and you're going to get interstitial condensation. If that happens, it's really good to have the material where that happens as a hygroscopic capillary active material that allows a little bit of distribution of that point of condensation. And certainly if it then has a drying path, it can then sort of dry out and it just reduces the peaks of moisture. So warm cell is very useful. It's very useful for that. One thing to bear in mind is that water vapor pressure might be going that direction, but if it condenses and turns to liquid water, it can actually travel in the opposite direction through capillary reaction, which is something that's quite important to think about as to why. Okay, so the risk here is that we do not have an internal vapor barrier. If we had an internal vapor barrier to reduce water vapor getting into the construction and a vapor open outside face to allow anything that did get through that to escape on the outside, you could use mineral fiber and we wouldn't have a problem with that at all. So a new building with I-beams and a vapor control layer on the inside, mineral fiber, fine. You know, although rats do like mineral fiber quite a lot, coming back to rats. But in this project, we have blocked gaping holes in the internal wall to reduce bulk transfer of water vapor through into the wall construction, but we haven't put a vapor barrier there. So it's potentially very sensitive to moisture building up somewhere. WUFI is great. You know, we're looking at a sort of idealized calculation. And there are always some areas, you know, maybe in a bathroom with showers, maybe there's a hole that hasn't been filled. There's a lot of water vapor able to get into the construction. We want to build in robustness. And hygroscopic materials like warm cell build in robustness and reduce the buildup of moisture in one particular area and allows it to dry back in or redistribute it as conditions around the assembly change. Does that answer it?
Yes, thank you. I needed that understanding, and I think I got from that condensation around the, for instance, a cold spot like a fastener. Yeah, could in fact lead to a rotting out of the material that fastener is attached to. Yeah. Okay. Yeah. Thank you.
Great. Thank you, Luke. So next up is Mick Woolley.
Hi. Yes, Mick Woolley. Hi. Yes, I've got my son's looking at a 1900 house that he's got. So from your presentation, I can see that you've got a fairly straightforward shape, and you've got a fairly straightforward construction. He's got things like character, brickwork on the front and back of the house, and he's got coving internally, and he's got the potential to put external wall insulation of some sort on one side, and I should say it's a semi-detached. But when you get to this sort of thing, I can see quite easily that we could do external wall insulation. He's quite, I think he's not keen on doing anything at the front, and I suspect he's not keen on internal wall insulation. Do we get any bangs for the buck at all out of doing part of the house?
Yes. Yeah. So this is very topical in the sense that, so we've done a project at a place called Cannon Pyne in Herefordshire, with a housing association, which is a historic solid walled house, or a traditional solid wall house with a 1970s extension and a stone wall. So we did do external wall insulation on the gable, the rear wall, and we put a high performance cavity wall insulation in. The front wall we did with internal wall insulation for very similar reasons that you just alluded to, and it works really well with the internal wall insulation. If you didn't have the internal wall insulation, you would get obviously a higher heat loss, and you would also potentially have some thermal comfort issues, particularly in those rooms I mentioned, the living room. So maybe you could choose the rooms in terms of thermal comfort. You could choose the rooms that might suffer from that and put a bit of internal wall insulation in. If you can't do either side of the wall, you are going to have a big cold lump, aren't you? And if it's a west-facing wall, maybe it'll be less less problems in terms of thermal performance. On this property I was talking about, it was a west-facing wall. We had internal wall insulation, and because we had sensors in there, we could see that the evening sun would heat the brickwork up, and about 8 hours later it would get through 9 inches of brickwork and it would reach the bedrooms on the other side. So in summer that was a problem. By putting internal wall insulation in, the benefit we got from that west facing wall was the bedrooms didn't overheat as much, but also the dew point never was reached in reality. It was predicted to have a dew point and condensation risk, which we'd managed through the way we designed the system. But that dew point was never reached because of the time lag of the solar energy getting through to the back of the wall about 11 or 12 o'clock at night. So, but at the end of the day, yes, you'll just have to take the energy penalty. There'll be increased greenhouse gas emissions unless you go to a heat pump and the grid is following up with decarbonised electricity. So I think it is worth doing. Wrap as much of the building as you can. Having said
Andy,
that,
I think this is going to be quite a common scenario, and I can picture it. Even in my village, I've been watching one and thinking, do you really know what you're doing here? You're putting a lump of insulation on the side here. You've changed your windows, but has there been a lost opportunity because you've done a lot, but
well, I'll tell you why it's so topical is because this social housing project we're looking at, it's got 70 homes. There's a mixture of bungalows and semi-detached. We're looking at the semi-detached group, and there are 30 in this group. It's got cavity wall insulation of some quality, and the pressure from the project was to put external wall insulation all around it. Now, some of those houses have got mock Tudor fronts. They've got a little bit of detailing of brickwork, and people don't really like seeing lumps of insulation shoved on the front. It looks ugly, people react against it, the community reacts against it. So we actually argued, we seem to have won this argument, that where the properties are already rendered or are ugly on the front, fine, put it on. But give tenants the choice. I like my brick wall. Give tenants the choice of not insulating the front wall. Insulate the sides, the back, the extension, attic insulation, do what you can on the ground floor, but leave and have internal wall insulation on the inside, not in this first phase of works, but later as part of the medium-term improvement plan. That'll be a later measure. So that has been popular as they do tenant liaison. They find that quite a lot of people saying, well, I would go for this set of improvements, but I don't want to cover the front wall. So actually what we've been arguing for, which has actually met some resistance because they want to just achieve the target. Now, in terms of how that performs as space heat demand, using PHPP, we are hovering around about 85 to 90 kilowatt hours after a full retrofit. So, you know, you're not at 50, you're not at 25, you're at 90. Now, the current government target for these projects is 50. They're going to change it to 90. 50 looks like the more sustainable target. So 50 plus a heat pump en masse would work. 90 plus a heat pump looks like it will be breaking the grid in 2050. So it's a bit of a challenge. Form factor, compact homes, easier to deal with, better, lower energy to run. Semi-detached and bungalows are going to be breaking the 50. They're going to be up in the 90s, really. If we didn't do anything, they're up at the sort of 150, 200. You know, well, they are if people heat their homes properly. People can live at passive house levels if they live at 12 degrees centigrade in the winter, you know. And when you talk to the national grid, they have a set of assumptions about how they will see heat demand reduce over time. Part of that is just a trickle of, you know, your typical energy efficiency, a bit more loft insulation and so on. But hidden away in their assumptions are people will heat their buildings less, people will only heat one room. Now they say, we don't understand about buildings, tell us, you know, we want to learn about buildings, but they've had to make some assumption about reducing demand whilst they increase electricity, decarbonized electricity production. So hidden away in their assumptions is people will be cold. People will be living in one room. Now that could be the reality of climate change and the energy crisis meeting the UK population, and I think it probably will be. So what we're doing now is really showing what might have been had we started in the 1970s and had political willpower to actually do proper building programs. So really it's catch up. How many people will we be able to help?
Yeah, thanks, Andy. Yes, very interesting points. And I can quite agree with some of that. I've got to go away now and convince my son to go for it. The good news is he does at least want to, his starting point was that he wanted to get to having a heat pump.
Well, I think that you've raised an issue which does need to be tackled, which is this cost of running heat pumps. So the government has signalled, hasn't it, that it's going to take the social costs off the electricity bill, and they're going to move it over a period of 10 years onto the gas bill, which means that electricity cost per unit will go down and costs of gas per unit will go up. But in the meantime, if you don't reduce the demand and you put a larger heat pump on, you will be paying quite a lot of money to run a heat pump unless you reduce demand. So if you've got the capital to reduce your heat demand to around 50, you should get a reasonable balance where some of the projects we've modeled show that aiming for the AECB retrofit standard does tend to find a balance where your electricity bill to run the heat pump at 250, 300% efficiency is about the same as what you're paying for gas. So it's not cheaper to run, but it's not more expensive. As your heat demand goes up, you're going to be spending more on your heating bills. Hope that was useful.
Oh, that's fantastic, Andy. Thank you. So Pete, I was actually wrong. Douglas is still here. Somehow I don't see him on the participants list, but he's definitely here. So Douglas, you're going to be up next. Before we get to your question, Douglas, I just wanted to ask Andy and Tim. We have a request for a link to the Herefordshire project. So if you have that link and could share it, I think folks would enjoy that. So Douglas, fire away.
Hi, thanks. That's very interesting. Small p political presentation. Now I just want to ask you, as from the point of view of people who live in apartments, are they really left out in the cold?
Apartments. We haven't done many apartments. There was another tranche in this social housing project which had more apartments. For some reason, I can't remember what the reason was, but the contractor who was employing us wanted to avoid those. They should be easier, I would have thought. You know, less surface area.
I've been involved in some, Andy, just to give some context. We've worked on a couple of projects, some to the EnerPHit standard and some to other, again, meaningful energy standards. But you need to get buy-in from the developer or the owner of the property, obviously. But the potential is huge. Like you said, Andy, it's actually quite a lot easier to make quite a big difference. You know, you have to obviously deal with a larger building, but if you can get buy-in from the developer or the owner or the council, if that's the case.
You mean do the block? Do the block.
Exactly. You'd have to really do them as a block. It's the way to go. But we have done quite a few of those here in Ireland, and they've been really, really successful.
There are some good examples in London as well of passive house retrofits to flats.
Could you comment on like heat pumps plus apartments? Well, you need the buy-in for that. I don't think you just get blockages otherwise.
Well, yes, that issue of heat pumps in apartments. So the AECB has a new build standard, and we do have a route for exemptions. We have had somebody recently who's had a very interesting conversation about can they claim an exemption and do direct electric heating in an apartment block, and the arguments are, well, the jury is slightly out on it at the moment, but you know, with small properties and the risk of overheating and so on, how hot water and heating is provided, it's not necessarily straight to, you know, having multiple heat pumps is not necessarily the best route. This is an area I'm slightly weak on. We have had some AECB webinars on it, and certainly for that sort of type of property, you could have a very interesting, more focused discussion around sensible approaches to, you know, when is direct electric heating more appropriate than heat pumps.
You know, that would be an interesting topic, because, you know, okay, I know the proportion is smaller of people living in communal buildings, but they still exist. So.
Yeah, for sure.
Douglas, the Rochestown Avenue project in Dublin is a good example. There's a lot of case studies online about that project. It's an EnerPHit retrofit apartment block there in Dublin, if you want to have a look at that.
Okay, great. Thanks a million. Okay.
Thanks, Douglas. Okay, Pete, you're up next.
Hi, Andy. Yeah, great presentation, guys. Quick question that you just touched on there briefly earlier. In terms of a lot of these social housing projects where there's a target of around 50 kilowatts per hour, the measures, EWI, CWI, doors, windows, ventilation measures seem quite attainable, but we often run into the issue with the floors. Did you have any ideas on, you know, ways to attack the floor to try and get those targets under 50?
Yeah, floors are the issue. So in the private projects, we've looked at, you know, working in shallow crawl spaces, and I know that the Qbot, the robot that sprays polyurethane foam with an operator, is something that's going to happen. I've got colleagues who've used it. In fact, we did some supporting research for them to help them profile their spray pattern so that it doesn't interfere with the moisture risks at the end of joists and sleeper walls, and they are having some good sort of results reported. And it's a kind of like, this is where the sort of needs of the circular economy, you know, not covering reusable, future usable components in foam that then compromises their ability to be reused, will become increasingly important. But it's far future stuff, this is. And so as a sort of straight fix, you know, sending a robot into a narrow crawl space and spraying foam on the underside of joists, it looks like they're starting to get, you know, pretty good at it. And when I'm sort of see a bit more performance data over the next couple of years, you know, I'll maybe be a bit more convinced by it. But certainly somebody I respect at Inhabit has been doing work analysing and monitoring, you know, what they've been doing, and she's very sort of supportive of them. So suspended floors, but we generally try to get a better result by taking the floors out and doing a proper solid insulated floor, with the issue that we then of course have to emit carbon for the concrete. And so the question is, you know, I think we're still at an early stage of understanding how much carbon budget can we actually invest in order to reduce operational emissions. And again, if we had more time, you know, decades more time, I think we'd understand how we would be doing that it is worth some relatively small upfront emissions to ensure, you know, 60 to 100 years of low operational energy, because it does dwarf it, you know, the emissions dwarf it, especially if the materials are becoming decarbonized. You know, you could invest quite a lot in a floor renewal to get high comfort and good performance, but we're not there yet. And it all seems to be about the next 10 years. So it really is a bit of a sort of hard thing to get your head around. My gut feel is we have very little ecological room. So I'm not quite sure where that leaves us. We might be back to the cold homes thing. On these social housing projects, there's a phase 1 set of works which is designed not to go in, not to decant the tenants. So we can do as much as we can on the outside. And then as part of the whole house plan, you have to say, what will you do when that property becomes empty and you can go and do something on the inside? And one of the solutions we are proposing is a thin aerogel layer with a magnesium oxide board on top. And it's basically just a 16 mil layer, which raises the temperature of these cold concrete floors and reduces energy loss, you know, sort of significantly. And so that's the plan, which involves cutting a little bit off all the internal doors just to accommodate that extra thickness. So there are sort of technical solutions.
That's great. Thank you. I haven't come across that aerogel solution. So that's great. Thanks.
All right, thank you. So next up is Stephen Howland, and Stephen doesn't have a microphone, I believe, so I'm going to ask the question on his behalf. And that is, if you insulate a wall externally or internally, and your neighbor doesn't insulate their walls also, could you accidentally increase a condensation risk at the party wall on the neighbor's side due to your wall now being insulated?
Yeah, but how significantly or worrisome that is, I'm not sure. I mean, we have kind of looked at that, and in the AECB Carbon Light training course, we do say be careful here, and part of that can also be, you know, there's no DPC in older properties, and as I said before, you know, maybe the sort of evaporation both sides of the wall is sort of right. If you know, perhaps tank a bit of the wall and put some internal wall insulation on, you could be then building up the moisture, and it evidences itself with salt damage on their plaster, you know, and if they put 2 and 2 together, yeah, potentially, for sure. I mean, all of these things make sense if you do the whole block. If a street of terraces just say, we're all getting together, we've got a new community group going, we're going to do all of this project at once, we're going to insulate all our attics, all our over rafter insulation, we're going to, you know, insulate the sides and the backs of the terrace, and we're going to do IW on the front, and they just get it together as a community. Everything, a lot of this hassle melts away, and they get a much better job. And really, again, our response to climate change has to sort of just become something completely different. And whether you think that's possible or not, I don't know, but that's kind of where the logic takes us. Otherwise, we are really making everything really, really difficult. And little details like this, you know, yeah, it'll put some people off. Some people who do it, there might be some neighbours disputes, but you know, it might be 5 years after the work's done. There's another question here, which is part of kind of relates to that, which I'd like to. That's Mark Perrins. He's saying he's got a cavity wall house, and he's putting some external wall insulation on and some internally, and he's saying, should I fill the empty 50 mil cavity? Absolutely, or at least stop air getting into that cavity from below and scouring heat out. So, you know, you should, yeah, don't have voids between insulation. Potentially, that's a big thermal bypass. It could be connecting to the cold attic. You know, it could have air bricks in it. There's all sorts of ways that is not a good idea. So definitely fill it. I would fill it rather than put insulation on the inside, to be honest.
Fantastic. Thanks, Andy. So next up is Alex Gahan, or Gahan. Sorry for the mispronunciation there. Alex, I see you on that. There.
Hi,
okay.
sorry.
Great.
Just struggling with my tech. I'd mentioned a couple of things. I just wanted to start by saying what a fantastic presentation. Thank you so much to everybody. And I love that comment made right at the start about the low energy and the meaningful innovation. I'm sure that's what the majority of us are here for. I certainly am looking to make changes to a 1920s house. It's brick. It's got lath and plaster on the walls, which is beginning to really bother me because I don't know whether I have to consider budgeting, taking everything, all that out. And I just wondered if the team had a project at all yet with lath and plaster and knew, how I should be tackling it. Unfortunately, I'm in a conservation area, so external cladding isn't going to work for me. And I have a shared access. I'm a semi-detached, so I'd be overhanging. Lots of complications, which means it's got to be internal. I had thought about maybe combining it with some soundboarding to help with insulation as well. But I'm just looking for who I should get involved in the project that might be a lath and plaster specialist.
If you clone Tim, he would be the person to get involved in that.
Right, okay.
And I think Tim should speak to that. But first of all, is the construction you're talking about, when you say lath and plaster, is that a solid brick wall with some internal stud work and lath and plaster? Because lath and plaster normally doesn't go on. Is that right?
Yeah. Yes.
Right.
Yes.
Okay. Tim, have you done anything like that?
Yeah, but it normally involves taking the lath and plaster out.
Okay. Yeah. And would you suggest that I speak to some form of conservation specialist?
The thing is, where are you going to put the insulation?
I think it's got to go internally on the
You thinking the other side of the lath and plaster or on the inside?
Well, lath and plaster would be sort of in the middle, and then the plaster would sort of cover it up. But I'm worried then about obviously moisture problems. Don't want to create issues because the house, although it's obviously not very energy efficient, actually breathes at the moment, and I am concerned about affecting that. But it sounds like I possibly need to come and speak to someone who knows what they're talking about. I wouldn't even attempt to do it myself, but I don't want to have anybody come out and look at it and say, oh yes, do this, this and this. And then 10 years down the line, I've got a really big problem and some structural issues on my hands.
It's interesting because the challenge is so big that you kind of want to, you as in me, as in look at the easy wins, the sort of ugly, houses where people really are struggling with heating bills, which tends to be the social housing sector. When you get to houses as challenging as yours, there are things you can do. It is expensive. It is subtle craft-based kind of approaches, using natural insulations and clever little techniques to increase air tightness without damage. It becomes a labor of love in a way.
Yeah.
So if I've got various colleagues and AECB members who are doing their labor of love on their properties, and there's a couple that we've been advising, but who are basically retrofitting their house. It's not a historic house, but there's a lot of these same issues. But it is an absolute labor of love. There isn't a nice, simple, systematic, affordable way of doing it. So you could probably start to nibble away at the problem if you're thoughtful, but yeah, you'll end up paying a professional and it will be slow and you won't get a huge energy benefit. So I suppose it might be worth thinking, why are you doing it? Perhaps, maybe you could be looking at air leakage, for example. Maybe that actually you can make a big win with just cutting out all those wretched drafts and getting a nice ventilation system in. And then looking at the size of the heat pump needed and think, well, is that worse than is the running cost of that worse than there's going to be some buildings which are just too challenging to do much to. And so you just got to look at where are the easy wins, how much will the heat pump cost? And as long as not everybody puts a massive great heat pump on, maybe there's going to be some buildings that are going to have to go in that direction or put jump on.
I totally agree with you. I think there are probably swathes of properties slightly different in nature, but will fall into that category. And so sort of a linked question I had for you, also with all the benefits and the great knowledge that you're getting from the projects that you're working on, but do you have loops back into government? Are you sharing with them what you're learning so that they really get a handle on how challenging this is? Because I think they've put the heat pump grant out there. They're not really even talking about EPC reforms. They're asking an awful lot of investment of people, and it just doesn't seem to be joined up. So,
well, it's interesting. Yeah, there's a disjunction between ministerial level, I think, and above, and civil servant level. So we have actually had 13 or so BAYS civil servants on our
Oh,
carbon light
brilliant.
retrofit course, which is nice.
Yeah,
And they are, and there are other groups engaging with them. And the PAS 2035 process has brought building physics right into that sort of zone. And in fact, you know, there's some people who've moved from the passive house sort of community, you know, one of whom in particular in my mind, who's working in a big government department at a senior advisor level now. And as I understand it, you know, a minister turned during a meeting and said, you know, this massive underperformance of buildings, is that a real thing? You know, and the advisor went, yes, it absolutely is a real thing. And the minister was going, my God, you know, I didn't realize that. So that's a moment that, you know, that minister might be replaced next year, and then it's all start again. But the civil servant is building, the civil service is building up an understanding, say within BAYS. I think they've got a good understanding, but I think the reality is that the Treasury is the entity that really holds our fate in its hands. And I think, you know, when you roll out that knowledge through programs like PAS 2035 rollout, I think it's severely compromised by people who don't understand what's needed, and politicians who don't have a serious intent to deliver something that works. That's, I think, how it is.
Yeah. Okay. I'm sure everyone else wants to ask. Andrew, thank you ever so much.
Thank you, Alex. We do have a lot more questions. I need to do a time check though with Andy and Tim and see what's realistic for you guys. This is we're an hour and 40 minutes into this amazing session. So what are you game to continue, or do you need to get back to your lives?
That's a good question. Tim, how are you placed?
I'm okay. I'm all right.
I did think somebody was insisting on a meeting, but a text seems to say that it's okay. So I think I'm all right says I'm all right till, you know, for another 15 minutes, perhaps.
Perfect. Okay, great. So the next question is from Eric Parks.
Hi, Eric.
Hi there, Andy. Hi, Tim. I think I've had a word with Andy about this before. It's a CWI related question, and Mark paired me, or any other CWI interested people may be interested as well. Did you do any kind of checking out of if there are any gaps essentially in the CWI before doing work? Because having done that to my own house in the last year, pretty great generally, but then there's clear spots like under doors essentially that are just, you know, gaping voids that I'm, you know, going to have to go back to and sort out. I was wondering what your thoughts were on that.
Well, that's good. Tim will have something to say on this. Because he did some boroscope, he did some work with a boroscope, but the client did do a thermal camera survey. Okay. I think on a day that was perhaps not cold enough. It did indicate that there were some areas of concern, but it wasn't definitive enough to know, is this a really bad job or just a sort of okay-ish sort of, you know, job. Tim, what did you make of the state of the cavity wall insulation?
Generally at that level, it was pretty good. We drilled holes about every half meter and stuck a camera in and had a look, and there were beads there. I mean, it's hard to tell what's going on in between or just above, obviously, but the fact that there were beads down at that level, a lot of them, was a positive sign. There were definitely gaps in other parts of the building. I think, do you remember that area we found, Andy, where they'd filled in an old garage door?
Oh, yes. Oh, no cavity at all there, was it?
It's just at all on that one,
yeah.
And then in terms of under the thresholds for ground floor doors, what...
The doors were brought out. The doors were brought out. Sorry, no, the windows were brought out, but the doors we actually set just off the top of the outer skin of the brickwork.
On compact foam.
On compact foam, but we had.
So you would have opened out and seen in the cavity, I suppose.
Yeah.
And was that filled? I mean, because that's in my mind, it seems like there's every kind of quote unquote, you know, certified guaranteed CWI job is missing these areas and has done for years and will continue to do so until something happens.
There's two ways the first threshold we found had no poly bead in it.
Yeah.
But you could feel to the sides, it had gone down. So the cavities were actually fairly clear down to the old 1950s foundations. Where the extension was built, it had more debris in it. I think it's part of the knocking through into the extension. Debris had got into the cavity. So at the south end, Tim, that was sort of the worst, wasn't it, in terms of debris at the bottom of the cavity. I think if there had been many gaps around that level, you would have imagined that air would have found its way in and got into the house. So to get an air test result of 0.75 kind of suggests it's not terrible.
Yeah. Okay. Yeah. No, good stuff. Thanks. And yeah, great to see this stuff. So
fantastic. Thanks, Eric. So next up is Akiboye Connolly. Hope I got the pronunciation correct there.
Yeah, this is Simon Connolly, and Caroline says hello to Andy and Adele as well.
Hi, Simon.
Hi. Our question was about the studs, the vertical OSB web framing that you used on the exterior. Did you find that the continuous OSB actually added up to quite significant cold bridging? Because we did a similar construction in a self-built studio where we used double studs, but we only had very widely spaced intermittent connections with plywood. So it worked like a Virendale truss in order to minimize the cold bridging spots.
Yeah, I quite like homemade trusses, which just have a few plates of plywood, but it generally, Tim, you find that in terms of like a contract on site rather than a self-build, that buying the I-beams about, is it 15 quid per 6 meter length or something?
It works out a lot cheaper than making them on site. Like to buy wood and ply and make them, it's a lot more expensive. I'd say it was probably 3 or 4 times more expensive than buying the I-joists.
But also the centers are 1200 centers. So in PHPP, we've put 1.5% in for the timber fraction of the web, because it's only 10 mil wide and they're only every 1200 centers. So actually the answer is no, there's not significant thermal bridging from that in this system.
So it's very modest. Yeah, our studs were at 600 centers, so there was a little bit more significance to them.
And don't forget, we've got the wood fiberboard riding over it as well, so that takes out the thermal bridging. I would say it's insignificant in this arrangement. Yeah. The more important is where 2 studs come together and insulation is forgotten to be put into the webs. Yeah. So I think the contractors also picked that up, didn't they, Tim? I think there was a period where they had not put insulation trapped in those little spaces, and then they realised and started doing it. Did you actually manage to get any in any of those missed spaces?
Yeah, we did.
Yeah, we used hemp fiber, and because that was very nice and springy, it would push itself into all the gap, into little voids in the double studs. Maybe using warm cell. While I'm on, can I just mention in relation to the Qbot sprayed polyurethane, we did an exercise on looking at the embodied carbon, the carbon footprint, assuming that it's a petrochemical based spray. And we reckoned that the carbon footprint was equivalent to about 17 years of heat loss. So we used, because we were very conscious of the carbon footprint, we lifted the floorboards, put cellulose fiber in between the joists on a breather membrane, and put the floorboards back.
Yeah, I think the reason that Qbot's raison d'etre is where a lot of floors need to be done and tenants can't be moved out. I think that, that's its niche, whether you agree with that or not. But in terms of the embodied carbon, under lifetime carbon accounting, my understanding is as well that these, some of those petrochemical foams do have a high upfront lifetime emissions for sure.
Yeah.
Okay, great. Thank you.
Thanks, Son.
Mark, are you here? Yes, Mark is here too.
Yeah, hi, I'm here, yeah. Sorry, my question was answered earlier.
Oh yes, that's right. Yes.
Oh, that's right. Okay.
Just on that, would you have any recommendation on how to close the cavity at the top, where it's quite irregular and
I'd close it at the bottom. I was thinking of closing it at the bottom, actually, and well, yes, and the top, because the air passage is cold air from the attic coming through into the house through the first floor joists, and possibly, is it a solid floor, did you say, or a suspended floor?
It's solid.
Solid floor. So air leakage is likely to find its way in from the attic down the cavity in through the loose joist sockets of the first floor. And of course, cold air is scouring heat. So your external wall insulation is being bypassed by cold attic air. And also air paths probably exist, a lot of them into the bottom of the cavity. And so that basically you've got a tunnel, haven't you, between the sort of ground and the cracks and fissures there up to the attic. So yeah, I guess you'd need to close the top and the bottom, or fill the entire thing. And I'd thought, I don't know, Tim, how expensive you found the poly bead installation, but you would have thought just filling the whole cavity with poly bead would be the best approach, rather than mucking about with a bit of foam, trying to be clever, sealing the bottom and then the top. Do you think?
Yeah, definitely. Yeah.
Yeah, and that bead would be sufficient to seal it at the top and the bottom.
Well, I think there are other factors, but when a few years ago, on that project I mentioned, a little village in Herefordshire, we did choose polyurethane foam injection to get a much better result for the cavity, but also to try to reduce air leakage. But I think what we might be seeing is that even putting in a blown material like a mineral fiber or a poly bead creates enough air resistance to be useful.
Okay. All right, thank you very much.
I'd risk it. Yeah, I think so. And the nice thing about poly bead, of course, is that it is vapor open, and if you do have any sort of moisture spots down sort of close to a sort of failed DPC, you have got a drying path following the vapor pressure gradient through the polystyrene beads and back into the house. I don't know what the external wall insulation is you're thinking of putting on.
EPS was what I'd had quoted.
EPS, so it's not closed cell, but it's fairly thick, so the vapor resistance will be quite high on the outside. So poly bead does allow some water vapor to maybe find its way back into the house, which can reduce risk.
All right, fantastic. Thanks, Mark. So Benny, if you are still on and would like to ask your question, I'll give you one more chance. Otherwise,
okay.
Yeah, okay, great.
Hi, sorry, I was just on an emergency call there.
No worries.
Boiler wasn't working.
Not at all.
Great presentation, guys. I've been following you all for years. Know Dara and Hugh very well. We've done bits and pieces of work together in the past. Andy, you've inspired me for years. I've been plagiarizing your work off your website and bringing it over to Ireland. So my quick question there really was: did you compare what a kind of your average normal rubbish retrofit would have been? I'll use that term now live, to what the cost of that one was, because I found that amazing now to put a timber structure outside of a masonry structure. I've never seen anything like that before, and I'm kind of a little bit involved in some of the retrofitting in Ireland, and I think we should be doing retrofit before new build, and I think the trades are going to start fighting for that, because there's not going to be enough to do retrofit and then new build. I think we should do up the